Okay, I'm going to assume that you had a chance to look over the PDF dealing with the idea of Jacobians, also known as Jacobians, if you like the Germanic here, but we'll call it Jacobians. Okay, and dealing with coordinate transformations. Okay, now, first thing, here's the idea of the problem here. We're looking in this case for a double integration of some integrand f of xy over a region of the xy plane. Now this may be a difficult integration, so our idea is to maybe have a change of variables, a change of coordinate systems, if you will, that will render an integral in that system which is easy to manage. Okay? And now a change of coordinates we called in our paper coordinate transformations. Okay? So let R be a region of the xy plane and T be a coordinate transformation given by this. T of u and v is xy. So x is a function of u and v, which I call little f here, and y is a function of u and v, which I call little g here. Okay, we're going to assume continuous first partial derivatives over r star, where r star is what? The corresponding region in the UV plane which transforms under T to the region R over which you're integrating in the XY plane. Okay, if the Jacobian is non-zero in the interior of R star and the function f of xy is continuous on R, then the double integral of f of xy over R is the double integral of f of little f of uv, comma, g of uv, so there I just made my substitution for x and y in terms of u and v, over r star, dA star is du, dv, or dv, du, depending on the order you want to integrate here. But the important thing here, let's not forget, is that I have the absolute value of the Jacobian, okay? You've got to include this in general for you to get an actual, a valid equal sign between the two of these, okay? Now let me emphasize here, this symbol is the absolute value of the Jacobian, okay? So using vertical bars, different people use different notations, so you have to be aware of that. The analogous theorem holds for transformations in 3 dimensions also. So we might have what Jacobian of x, y, and z over u, v, w, say. Okay, now let's go ahead and actually first compute some Jacobians. Let's say I was going from cylindrical to Cartesian coordinates, okay? You know that's going to be x equals r cosine theta, y equals r sine theta, and then z is just plain z, right? Because cylindrical coordinates have coordinates r, theta, and z here. Let's go ahead and compute the Jacobian for this case here. Okay. Okay, here's what we do. We take r here and we differentiate it with respect to the coordinates in their proper order. Okay, so I'm going to differentiate x with respect to what? R. So I'm holding theta and z as constants. So the partial derivative of x with respect to r would just be cosine theta. Okay? And then do it with respect to theta, holding the other two constants. So that would be minus r sine theta. Okay? Then differentiating with respect to z would yield what? 0. Okay? Now do the same thing with the y on the second line. Okay? With respect to r, that's the sine of theta. Okay, with respect to theta, that would be r cosine of theta. And with respect to z, that would also be 0. Okay, so these are our 3 independent variables here. Coming back to the very last one here, the partial derivative of z with respect to r, since these are what? The independent variables, we would get what? 0. With respect to theta, we would get 0. And with respect to z, we would end up getting 1. Now, this is going to be actually an easy determinant to actually work out here. I'll expand down the third row or third column, I guess. Okay, so remember how it goes with computing a determinant: plus, minus, plus, minus, plus. So this is actually, would be this. 0 times the determinant found by getting rid of the first row and third column, r cosine theta. I guess these would be zeros. And then, so it goes plus, minus, plus. So I've got a plus in front of there, so it's really subtraction. Minus 0, get rid of the third column in the second row, we would get what? This determinant, this subdeterminant. Okay. And then plus the very last one, 1 times getting rid of the third row and third column, we have cosine theta negative r sine theta. Sine theta, r cosine theta. Okay. You can see these are going to zero out. What's this one going to be? R cosine squared theta minus negative r sine squared theta. So you can see, because cosine squared plus sine squared is equal to 1, then we've got what? R. Okay? Now the absolute value of this thing would be absolute value of r. If we make sure r is going in the positive direction when we integrate anyway, then we could just write the absolute value of r, which is presumably going to be r. Okay? Now, that means, so if you're looking at a conversion from Cartesian to cylindrical, so this would be in 3 dimensions, you'd be looking at this, right? A triple integral over r star, whatever that would be. I guess I would call it a solid. Let's call it s star instead of a region, because this is 3 dimensions. Some function of x, y, and z, so it would be what? R cosine theta. That's f of x, y sine theta, and then z. And then what would we have here? We would not forget to put in the absolute Jacobian, so it would be r. Now, different orders you can integrate in dz, dr, d theta. It's a typical direction here. Okay, so you see where that r is coming from. All right. All right, let's take another example here. And I just wrote this out for you. I guess I still called this example 1 here. But what if you're dealing with spherical coordinates? Okay, this is going to be a little bit uglier here, as you can imagine here. Okay, remember spherical coordinates in mathematics, we use what? Rho, theta, phi. Okay. By the way, in physics, I forgot to mention this, they interchange the definition of theta and phi. So if you're looking in books in physics and possibly some engineering books, you might find these are actually have the opposite meanings. Okay? All right, we're going to do it the math way, though. Remember that x is what? Rho sine phi cosine theta. Y equals rho sine phi sine theta. And z equals rho cosine of phi. Okay? So here's our coordinates in this order. These are the independent variables, right? So when you take partial derivatives, what do? For example, if you're going to take partial derivative with respect to rho, be sure and leave these other 2 fixed and so forth. Okay? So here, in the first row, you're going to be differentiating with respect x with respect to rho, and then what? With respect to theta, and then with respect to phi, and then you're going to do the y line, do the same thing, and then the z line here, okay, the 0. Okay, 0, not 0, 0, okay? And then you have to find the determinant of that 3 by 3 matrix. You can see here I've just written out the details. I didn't want to go through all this, but you can go through this in depth if you want. What you're going to do, actually simplify down here, is you're going to use the Pythagorean identity, cosine squared of an angle plus sine squared of an angle equals 1 a couple different times. Believe it or not, all this boils down to a final determinant, which is minus rho squared sine phi. Now, we're going to take the absolute value of that. So the little Jacobian factor we're going to have in there when we're dealing with what spherical coordinates is going to be what? Rho squared sine phi, right? Rho squared sine phi, you're familiar with that. So typically we'll have differential volume being rho squared sine phi d rho d theta d phi, or d phi d theta. So a lot of times I'll turn these around. Okay, alrighty. So there it is, kind of long and arduous here, but it's really doable. You remember this fact about when you're interchanging any two rows or columns in a determinant, by the way, that changes the signature of the final answer, okay? So you could consider this minus sign here just an artifact of the order in which we've taken our coordinates, okay? All right, let's look at another example here. Okay, let's go ahead and take a look at a second example here. Evaluate the integral I, which is the double integral over r of xy cubed dA. Okay, let's take a look at the region first, where the region R is bounded by these following curves. Xy equals 1, xy equals 3, y equals 2, and y equals 6. And we want to use this transformation up here so that x is v divided by 6u, and y is equal to 2u. Okay, and then we'll look at the solution. Now, before I look at the solution, I went ahead and actually graphed this on Desmos for you. Okay, now you can see that I've got these lines y equals 6 here and y equals 2. Okay, and then these two other curves here are what? xy equals 3 in blue and xy equals 1 in orange. Okay, or red, I guess it is. Okay, and so this is the region over which we're going to be integrating. Now, that doesn't look particularly difficult to integrate over in regular Cartesian coordinates, but we're going to go ahead and use this transformation as to get us some practice in using Jacobians here. But this is the critter, or R, that we're integrating over, so I'll call that shaded area there, that thing R. Okay, you can tell that these are xy equals 1 and xy equals 3 are what? Hyperbolas, right? Okay, and in fact, let's go ahead and see this. We can see very clearly that those are going to be what? Those are going to be those horizontal lines in the graph here. Let's look at xy equals 1. We want to transform that curve into u and v curves, okay? So this is going to be equivalent to, let's see, now what is x? X is v over 6u. Y is 2u. So, and this is supposed to be identically 1. So let's see. This would be what? The u's would cancel. And that would be 2 divided by 6 is 3. So this would actually be, if I multiply on both sides, v equals 3. What's nice about that? Well, what's nice about that is that what? This is going to be a horizontal line in the, or a vertical line, I should say, in the UV plane. I'll make u the horizontal and v the vertical. So there we go. Okay, axis that is. How about this one? xy equals 3. This would be equivalent to what? Well, it's almost the same. We're just going to have what? V equals 9 this time. Instead of 1 on this side, we have 3. So it's going to be v equals 9. Okay. So I guess this would be what? If v is the vertical, this would be a horizontal line, and so would this. Yeah, I was right the first time. How about these ones, though? Y equals 2. That would be equivalent to saying, well, what's y again? Y equals 2u. So I'm saying 2u is equal to 2. That would be equivalent to u being constantly 1, wouldn't it? Okay. Remember, this stands for what? The set of all points x, y, such that y equals 2. This ends up being the set of all points uv such that 2u equals 2, which is the same as u equals 1. How about this one? Y equals 6. That means 2u equals 6, so that means u is equal to 3. Okay. Alrighty. So, if I call this thing R, and this is my transformation, and I'm worried about this second region R star such that T of R star is equal to R, then it would be what? The boundaries would be these lines. Okay, so let's go ahead and draw this in the UV plane. Okay, so we've got V is equal to 3 and V is equal to 9. Okay, my drawing may not look so great here, but it should be. It should be okay. Equals 9. And then we got what? 1. U equals 1, I should say. U equals 3. Okay. So these are the boundaries. Yeah, these are the boundaries. So what's my R star here? My R star is this thing right there. There's R star. Okay. So if I take T of R star, I would get back this funny region of the XY plane. Now, what do we need to do next? Okay, the next thing you want to do before setting up your integral, right, rewriting this in terms of U and V, I've got to remember that I need the absolute value of the Jacobian, right? Okay, so let's go ahead and do this. What's the Jacobian for this particular problem? Okay, remember, maybe I should review this, write it explicitly. I mean, we did this in the previous problem, but problems. Okay. By the way, if you did get the rows and columns mixed up here, so you essentially took the transpose of that matrix, the determinant of a matrix and its transpose are going to be exactly the same. You would still get the right answer in the end. Let's go ahead and do this though. All right, let's see. Now x is what? V over 6u. Now I'm going to be differentiating that with respect to u. So what would we get here? We would get negative V over 6u squared, right? Because that's really thinking about that as being u to the minus 1 power, right? Okay, so that's our x. Okay, and you're holding V is constant in this one, and this one you're holding u as constant. So if I differentiate that with respect to V, what do I get? 1 over 6u. Okay. Now let's go ahead and work with the y. Y is just 2u, so this should be fairly easy. So this would be what? 2. Okay. What would this be? What's the derivative of that with respect to v? Yeah, it's 0 because I'm holding u as a constant, right? U and v are the independent variables. So this is the critter I'm looking at here. I need to find this determinant. And what do I get here? I would get product here is 0. The product here would be 1 over 3u. So that would be negative 1 over 3u. And then I'm going to be taking absolute values here. So this would be 1 over 3u. Okay? This is, I'm going to have u going in the positive direction here. Okay, increasing u when I integrate, and you can see it's going to be positive over my region. So the absolute value of 1 over 3u would just be 1 over 3u for our problem. Okay, now let's go ahead and write my integral I. Well, this is the original. Okay, I want to write it in terms of u and v. Okay, so remember I'm going to be, let's maybe start like this. Remember it would be this. Okay, I'll put it in the details there in a second. What is x? See, I've got xy cubed. So that's going to be what? X y cubed. Okay. What do I want to include in here? Don't forget, from our original theorem, what I still have here, I need that guy in there, right? Okay. I need absolute Jacobian in there. So I'm going to put in there what? 1 over 3u. Then I'll go dA star. So that's du dv or dv du. We'll decide here in a minute. Let's take a look at the integrand here. Okay, so it looks like I have 8 u cubed in the numerator, and down in the denominator I have 3 times 6 is what? 18 u squared in the denominator. Okay, I think that's right. Then we've got a v sitting there. Okay, and then what? Shall we go just for kicks? du dv? Okay, all right. Let's put the limits of integration in. Where is u going from and to? U is going from 1 to 3. And v is going from 3 to 9. Okay, we're just integrating over a rectangle in the UV plane, so the order isn't going to matter that much. Well, it isn't going to matter. It's going to be easy to do either way is what I'm saying. Okay, that's really a u, isn't there? What do we have there? Does that reduce to 4/9? Is that right? Okay, u, v, du, dv. Okay, we're integrating with respect to u first. Let's maybe take the 4/9 outside. Okay, let's not write an equal sign. Let's just do the inside separately. Take the 4/9 out. Let's go u du, and then don't forget we're going to multiply by v in the end. We could actually break this up into 2 integrals. You see, it's just a product of 2 integrals. You want to do that? Yeah, we could actually do this time, couldn't we? That way I can do this maybe a little bit faster. Okay, see how the integrand is just a product of u and v? So I'm integrating with respect to u. I could write that as a separate integral. That would give me a constant value. Then I would integrate v with respect to v here, going from 3 to 9. I could just do these separately like that. I will write an equal sign. So that would be an easy way to do it. Let's get through this though. That's what? 1/2 u squared from 1 to 3 times 1/2 v squared from 3 to 9. Okay, that becomes a quarter right here, so this becomes a 1/9. So that's 3 squared, which is 9, minus 1 squared, which is 1. 9 squared, 81, minus 3 squared is 9. Okay. I'll take the 9 and divide it in both of these, so I would get 8 times 9 minus 1. So 8 times 8 is 64 for our final answer. Okay, so there it is.